Hi, my name is Elijah Martinez, and I'm a part of Group 1, and this is the lab report on Lab 6. Every day, we see objects moving through the air, which may look simple on the surface, but are actually shaped by some beautifully consistent physics. Whether it's a basketball arcing towards a hoop, a fountain shooting a stream of water, or even a firework shooting into the air. All of these motions follow the same underlying principles. This curved path is known as projectile motion, and it's exactly what we're going to be exploring in this lab. In our experiment, we'll be focusing on how a steel ball behaves when it's launched from a mini launcher. At first glance, the path looks complicated, but physics gives us a powerful way to break it down. At first glance, the path looks complicated, but physics gives us a powerful way to break it down. Instead of treating motion as one big problem, we separate it into two different components. One of those components being horizontal, which stays constant, and the second component being vertical, which accelerates downward because of gravity. Even though these components act independently, their combination creates a trajectory that we can observe. Scientific literature on projectile motion going all the way back to Galileo shows that the independence between horizontal and vertical motion is key to predicting where a projectile will land. Physics and engineering texts emphasize that by using kinetic equations, we can calculate important quantities like initial velocity, time of flight, and range, even when we can only measure some of the final conditions. This is exactly what the approach that we're using in this lab, measuring what we can and using physics to determine what we physically cannot observe. Projectile motion isn't just a classroom idea. It's used consistently in real life. Engineers designing water fountains, such as the one you might have seen in Las Vegas, rely on these equations to control when the water shoots and how far the water travels. Athletes and coaches analyze projectile motion to optimize throwing angles in sports, like football and track and field. Even video game developers use these same principles to recreate realistic gaming interface. In this lab, we will apply these concepts to determine the launch velocity of the mini launcher and use information to predict where the steel ball will land at different angles. By understanding the physics behind this motion, we can turn a seemingly complex path into something predictable, measurable, and incredibly useful. Now I will hand it over to Daniela, where she will then explain the materials used in this lab and how we use those materials to get our units that we used in the equations to figure out what the final velocity is.
Hi, my name is Daniela Avila, and now I will explain the materials we used for lab number 6. For this lab, we use a mini launcher to shoot a small steel ball. This launcher helps us to study projectile motion and understand how objects move in the air due to gravity. We also use a steel ball, which is the object we launch in every trial. We repeated the experiment several times to make sure our results were more accurate and reliable. To measure distances, we used 1-meter wooden rulers because we needed to know how far the ball landed from the starting point. We measured each trial carefully and then calculated an average distance to reduce error. We used paper and carbon paper to mark the exact landing position of the ball on the floor. This helped us clearly see where the ball hit after each launch instead of just guessing. We also used tape to fix the paper on the floor so it will not move during the experiment. This was important to keep our measurements consistent and avoid mistakes. Additionally, the launcher has a protector which allowed us to set different angles like 30, 45, and 60 degrees. So changing the angle helped us compare how the distance changes depending on the angle of the launch. Finally, we use a calculator to solve equations and find values like time, velocity, and distance. Overall, all these materials were very important because they help us measure, calculate, and better understand projectile motion in a clear and organized way.
Hello, good afternoon. My name is Dave Maldonado, and I am in charge of the procedures for lab number 6. Our objective for today is calculating velocity at which a manual launcher launches a steel ball to calculate and predict whether this will land at different angles, utilizing a total of 4 different angles, I believe so. Our equation will be final position equals half of acceleration times time to the second power plus initial velocity times time plus initial position. This is our equipment setup. The real challenge for our procedure is the initial point at where it lands, as it's kind of a guessing game. So we have 3 different non-zero angles plus the 0 angle at which we started for initial positions. This is our setup. So we have the metal weight, which is going to be this part right there. Our protractor is going to be right here, which measures our angle. Our launching point will be that. Our range setting is this, which is what we use. And our lanyard is that. Typically for the range setting, we put it to 2 clicks. And then for our lanyard was our kind of our trigger. So then we will get all this information. We'll get the initial position by X and Y coordinate. Our final position by X and Y coordinate, which is 0 meters. Our initial velocity, acceleration, and our time. To calculate the time and initial velocity, we will use the equation T equals square to the square power ty to the initial over negative acceleration y. We'll then get 2, which is our muscle velocity, which is Fx equals Fm. These are the next steps. So we'll set up our mini launcher to 30 degrees. After this, we'll measure our initial velocity. We'll use our muscle velocity, which again is Vx equals Vm cos delta, Vy equals Vm sin delta, or theta, my bad, theta. Our time of flight equals A equals negative 2A, B equals Vy, C equals Y0, or time equals the quadratic formula. And then we'll use our theoretical final position, which is X half equals Vm cos theta t. After this, we'll shoot our carbon paper a total of 5 times at that angle. We'll measure our distance from the vertical line. We'll repeat steps 1 through 6 a total of 3 times with the angles 45 and 60, as well as 30. And then we'll also be getting our percent error, which is going to be this one right here. Percent equals theta x AV over XF 100, which we will then put into this table right here to calculate our percent equal, theta equal distance, experimental distance. Here are some reflecting questions we asked. Where do your percent errors come from? Do you think there are factors affecting your experience not considering the formula we are using? Which ones are they significant? Do you think there is a way to minimize that error? Are all your percent errors equal? Why or why not? Dave Maldonado. I am once again in charge of the procedures for lab activity number 6. Thank you.
This is Alejandro for data and data analysis on lab 6. For lab 6, we have 4 different launch angles, one at flat, one at 30 degrees, one at 45 degrees, and one at 60 degrees. For the flat angle, we got a height of 0.98 meters. The first launch was 1.96 meters. Second one was also 1.96 meters. The third one was 1.961 meters. Fourth one was 1.962 meters. And the fifth one was 1.967 meters. These are the numbers we plug into our chart. The initial position had an x of 0 and a y of 0.98. The final position was 1.962 meters and a y of 0. The initial velocity had an x of 2.151 meters per second with a y of 0. And the acceleration had an x of 0 with a y of 9.8. Our next step is to get our t, our time, which is the square root of 2y divided by g. We get square root of 2 parentheses 0.98 divided by negative 9.8, which gives us a total time of 0.44721 seconds. Next, we get our average position, which is 1.96 plus 1.96 plus 1.961 plus 1.962 plus 1.967 divided by 5, which gives us an average position of 1.962 meters. Using our average position and our time, we get our VO, which is 1.962 divided by 0.44721, which gives us a total of 4.389 meters per second. For the next part, we move on to our different launch angles of 30 degrees, 45 degrees, and 60 degrees. For each of the angles, we have to get a VOX and a VOY. For a degree of 30, we plug in 4.389 cosine 30, which gives us a VOX of 3.8. And then for VOY, we plug in 4.389 sine of 30, which gives us a VOY of 2.194. For the degree of 45, we plug in 4.389 cosine 45, which gives us 3.1035 meters per second VOX, and then 4.389 sine 30, which gives us a VOY of 3.1035 meters per second. For a degree of 60, we plug in 4.389 cosine 60, which gives us a VOX of 2.1945 meters per second, and a VOY 4.389 sine of 60, which gives us 3.8 meters per second. Then we get a time for each of our angles using t equals negative b plus or minus square root of b squared minus 4ac divided by 2a. For the degree of 30 angles, we got a time of 0.737 seconds. For our 45 degree, we got a time of 0.882 seconds. And for the degree of 60, we got a time of 0.999. For our XF theoretical, we use our VOX and our time. For the 30 degrees, we use 0.737 times 3.8, which gives us a XF theoretical of 2.8 meters. For 45 degrees, we get 0.882 times 3.1035, which gives us an XF theoretical of 2.76 meters. For 60 degrees, we use 0.999 times 2.1945, which equals an XF theoretical of 2.19 meters. Now that we have our XF theoretical, we can actually launch our attempts. For 30 degrees, we had a first one of 2.735. Our second launch was also 2.735. Our third launch was 2.725. Fourth one was at 2.720. The fifth one was at 2.717. For our 45 degree angle, we got our first launch at 2.605. The second launch was at 2.64. The third one was at 2.645. Fourth one was at 2.646. And the fifth one was at 2.647. For 60 degrees, our first one was at 2.155. Second one was at 2.164. Third one was at 2.164. Fourth one was at 2.173. And the fifth one was at 2.174. Next, we get our averages for each of the angles. For 30 degrees, we're at 2.726. For 45 degrees, we're at 2.637. And for 60 degrees, we're at 2.166. Lastly, we get our percent errors for each angle. For our 30 degree percent error, we're at absolute value of 2.726 minus 2.8 divided by 2.8 times 100, which gives us a total percent error of 2.64%. For our 45 degree percent error, we're at absolute value of 2.637 minus 2.76 divided by 2.76 times 100, which is a percent error of 4.46%. For our 60 degree angle, we get the absolute value of 2.166 minus 2.19 divided by 2.19 times 100, which gives us a percent error of 1.1%.
To summarize, we launched a 16mm steel ball out of the mini launcher provided to us several times from different angles, those angles being 30, 45, and 60, aimed upwards in order to get our answers. Based on our answers, we should be getting around 100 extra credit points. Out of error percentage came out to be less than 5%. The extra credit points being from 10 points from RVO, 30 points from each error percentage, and we got 3 error percentage answers.